Thanks very much. Good morning, everybody. Today we're going to be talking about Amazon Elasticsearch service. We're going to do a little bit of a deep dive into the service and into Elasticsearch itself. And we're going to approach this from the perspective of a small company, if you will, or it's the scenario that you can imagine where a small video company wants to provide search over some movies. They want to be able to sell those movies to their customers, and at the same time, they really want to be able to make sure that their application is working and everything is up and running. They hear about Elasticsearch and they think, oh, Elasticsearch is pretty cool, I hear. You know, Elasticsearch is a tremendously popular piece of software. It has been out for about 8 years now, and we're looking at the TechCrunch survey here of popular open source software. You can see that Elasticsearch is sitting at number 7, and there are a number of reasons for that. First of all, it's open source software, so it's out there for you to download and use. There's fast time to value. Elasticsearch itself, pretty easy to get started with, easy to get data into it. You can do some really cool visualizations and analysis with it. You can search your data. So it's fast time to value, and it's really, you know, gives you an easy start on this problem. And our mythical company also appreciates the ability to search their application data and monitor their infrastructure. So with Elasticsearch, again, you can both provide your application search and also monitor it as well. And we're going to go into depth on both of these pieces of the equation. We're going to look at application search itself, as well as how to set up for and monitor your infrastructure. Now, our mythical company gets going with Elasticsearch. They find everything's working really great. In fact, their business is growing really quickly, and they come to a scale or an inflection point, and they find out you know, where Elasticsearch is easy to get started. Sometimes, as you scale up, it can be difficult to operate the infrastructure you need and monitor it and make sure it's secure. And so, you know, we also heard this story from many customers, and we have offered Amazon Elasticsearch service as a way for you to deploy and use Elasticsearch in the AWS cloud with ease of operation, making it easy to deploy, manage, and scale that Elasticsearch cluster. We also have integration with open source so that you can easily have the same experience with Amazon Elasticsearch service as you do with running Elasticsearch yourself. Some of the other things that we provide, number one, again, we support that open source experience. So both in terms of the Elasticsearch APIs that you'll be calling, as well as some of the tools that you have around Elasticsearch, like tools like Kibana or Logstash. Those all work with the service out of the box. It's easy to use, so we make it very simple for you to get Elasticsearch clusters deployed in the cloud. It's a process of going through the console, the SDKs, the CLI, any of those methods, CloudFormation, you specify some of the parameters that you want in your cluster in terms of the instances, and we go off and deploy that hardware for you and own and operate it. The solution is a scalable service, very scalable. So if you decide that you want to have more instances to run on, or you decide that you'd like to change your instance types or change out the storage, we make it easy again with a simple API call or console interaction to scale and right-size your cluster. We provide security options. We'll go into depth on those, but we do make it easy to secure your data within your Elasticsearch cluster. Also, we have high availability features that make it easy for you to deploy across multiple availability zones within AWS. And then finally, we have a number of integrations with other AWS services that provide you, number one, easy ingest of data, and number two, easy monitoring and alerting on your Elasticsearch cluster itself. When you use the service, you deploy what we call an Elasticsearch service domain. A domain wraps hardware and software needed to run an Elasticsearch cluster. You deploy that domain again through the console, SDK, CLI, or CloudFormation. We spin up a set of instances for you. Elasticsearch instances within the service come in two flavors. There are data nodes and master nodes. Data nodes hold data and respond to updates and queries. Master nodes are orchestrators of the cluster. We'll have more detail about that too. We front the cluster with an Elastic load balancer and then provide you with an endpoint, which is resolved through DNS, and you interact with the Elasticsearch APIs over that endpoint with the cluster underlying. You secure your endpoint in a number of different ways, and the first of those is IAM, and the second is VPC. Now, our hypothetical company is aware of the service, but before they can actually figure out what kind of architecture they want to deploy, they have to think a little bit about security. So let's take somewhat of a detour here and look into the different security possibilities. So the first of these, again, with Elasticsearch service domains, you get an endpoint that you resolve through DNS, and that's where you communicate with the Elasticsearch cluster. You have two choices for where to put your endpoint. You can have a public endpoint. This would resolve through DNS to a publicly available IP address, or you can have a private endpoint, which would resolve to an IP address within the address space of your VPC. For public access, anybody on the internet can access that. We see that as being useful in cases like a mobile kind of application where you want everybody in the world to be able to communicate with your cluster, whereas VPC we see as being a higher security option where traffic to your cluster is limited strictly to known traffic within your VPC. VPC is our recommended solution. However, public endpoint is perfectly viable. With a public endpoint, you use IAM. Again, you write a policy to secure that endpoint. With VPC, you can either use an IAM policy, security groups, or both. And of course, in the realm of security, we do support encryption for your data. So let's have a little bit of a look into that. For public endpoints, again, we recommend setting an IAM policy so that your Elasticsearch domain is not open to the world. There are a number of different pieces of the policy. One usual use case is to use Kibana. And using Kibana, you need to come from a particular IP address. So we recommend writing a policy that allows all access from that particular IP address. And you can do that with a condition on your IAM policy. For read-only access, and this would be for a front end of the application, again, that mobile kind of situation, you would add an ES HTTP GET action to your IAM policy. So the actions that we support include the HTTP methods that you use to communicate with Elasticsearch, as well as the administrative calls that you use to create Elasticsearch domains and scale them. Then we also have a resource portion of the condition. The resource controls what access you have to the underlying data in Elasticsearch. So for the resource, you can specify it as a particular domain, an index within that domain, or indeed even API calls, Elasticsearch API calls for that particular policy. For admin access, we do recommend a policy that kind of leaves it wide open. We do find if you're going to administer the domain, generally you're going to want to do all of the actions that you can possibly do. Within VPC, you can also add security groups to control access based on the IP addresses of the contacting entity. We support your VPC through launching Elastic Network interfaces into your VPC itself. You then communicate with those Elastic Network interfaces and the traffic gets forwarded to Elasticsearch service. And finally, again, we do support encryption of data at rest. This is for both EBS and ephemeral disks. And that encryption is provided with integration to KMS so that you can provide your own keys. We additionally take automatic snapshots of your domain, and those will be encrypted if you choose this option as well. So coming back to our XYZ company, let's talk a little bit about the front end and the web application that they are running to search movies. For this particular architecture, and again, given that we're launching into VPC, we have traffic coming from the front-end servers. These are clients who are hopefully going to be buying our movies. They go through an internet gateway and then through an application load balancer to a set of EC2 instances that's auto-scaled and that's running Apache HTTPD. It's a very simple application. It's written in PHP for this example. And that application takes a couple of search keywords from a customer. It formulates a query for Elasticsearch. It sends that query to the Elastic Network interface, and that gets forwarded to Elasticsearch, which replies with the search results. The PHP then formats those search results and puts the page up for the customer to see. When we deal with the search engine, the core concept is the search document. A search document is the entity that you put into a search engine, and it's the entity that you retrieve when you run a search request. Documents, and this is an example of a particular movie, comprise a set of information about the underlying entity. So in this case, if we're looking at Iron Man, we have a lot of different fields in here, and the document itself is somewhat structured, right? So we do have one thing, which is the Iron Man movie, and then within that, we have a number of different fields that we'd like to search in. Things like the title and the actors, the directors, a rating is often useful. When you use Elasticsearch, Elasticsearch itself provides you search at a fielded level. So you start off with this single entity that you want to retrieve, and then you have to cut it up into a set of fields that comprise individual pieces or values that you want to look at. When you format that data to send it to Elasticsearch, you send it to Elasticsearch as structured JSON. So I have my fields that I've identified in my original document. I format those with field names and then values for those fields. And you can see here we have a title and a plot, the year the movie was released. We have some actors, and notice that we can have multiple value fields, so we have more than one actor here. Each of those actors then is available itself for query or for retrieval. We have directors, rating, genres, etc. Elasticsearch also does support a nested JSON structure natively. So if you have any hierarchy in the objects that you're sending in, you can encode that in the JSON. Then underneath the covers, at a field level, Elasticsearch creates an index. So if we picture our document as a set of fields with names and values, then for each field, Elasticsearch analyzes the value and then creates an index for that field. The index contains every single value that has been in that field for all of the documents that have come through. Right, so for example, the field index here, if this were the actor field, one of the entries here would be Mark Hamill. Now it's actually a little bit more complicated than that because Elasticsearch works with both full string matching as well as language analyzed string matching. So for something like a plot, Elasticsearch would, and I would have to specify this as a field type, Elasticsearch would go into that big string, cut it up into individual words. Those would be called terms, and then the individual terms would be stored in the index. So if I send a query that included the word Luke, because Luke Skywalker is the start of the plot, if I send a query with the word Luke, Luke could then match to the plot field of Star Wars. The indices themselves then are a list of terms, and then each of those terms points at a posting list. The posting list contains the ID for every document that contained the term, that term. So if the first term there was Luke, then I would have a list of every document, in other words, every movie that had the word Luke in the plot. Now, those are the field level, but in fact, at the higher level, we have an index that contains all of our documents. So I'm sending my documents in. One of those is going to be Iron Man. One of those is going to be Star Wars. I'm sending those documents in, and they are organized into an index. We could have an index like movies that contains all of my movie objects. We could have an index like actors that contains all of the actors separately. Or we could have a index of users, people who are using my application. That index is logically broken into what are called shards. A shard is a subset of documents from the full set of documents in the index. So if I have 5 shards, each of those shards has 20% distinct from every other shard of the documents in the index. Shards can be primary or replica. So a primary shard is just the first instance of a shard. Once I set my primary shard count, that's fixed for that index for all of time. I can't change that except asterisk in later versions of Elasticsearch, but we won't get into that. I can also have replica shards. A replica is just a copy of the primary. The first replica shard gives me redundancy so that my data can be deployed to 2 different locations in the cluster. And additional copies or additional replicas do provide me more query capacity. And it's very important, primary and replica shards are actually distributed to different instances in the cluster. So the primary copy of the data and the replica copy of the data never sit on the same instance. And that's how I get that redundancy. If I lose an instance and I lose either a primary or a replica, the data itself is still within the cluster and I can still recover that data into a second copy. So as we deploy our data, I want to say a few words about sizing. Sizing is a tremendously complex topic and very tailored to individual workloads. But there's a few things we can say at a high level that help with getting started with sizing. So the first thing is, as you create a cluster, you need to think about how many instances you want to have in that cluster. And one very easy way to get a handle on that is to think about how much storage you need in the cluster, because at least you need enough instances to have enough storage online to hold all your data. So as you're sending your data into Elasticsearch, as we said, Elasticsearch is indexing that data and creating data structures out of it which are not one-to-one. In fact, your source data will create an index of a different size, and usually we find that to be about 10% larger than your source data. Now, the nice thing about that is, as long as you leave yourself a little overhead, you can kind of ignore that inflation and just say that the index size is approximately the source size. Now, for each replica that I deploy, I'm adding, again, that amount of storage need. So, for example, if I have a 2 terabyte corpus, then when it becomes an index, we guesstimate that it would be 2.2 terabytes, but to simplify things, we just say, okay, that's about 2 terabytes. Then I'm going to have a replica of that data, so that's an additional 2 terabytes that I need. So I need a total of 4 terabytes of storage to hold my 2 terabytes of source data. And assuming that we're using EBS, our maximum EBS volume size is 1.5 terabytes. So I'll need about 4 instances. We can see this by saying, okay, well, we need 4 terabytes, and 4 instances gives me up to 6 terabytes. So I can just divide it out and say if I deploy 1.5 terabytes each or 1 terabyte each, I'll have enough for storage. When we think about instance type is where it gets a little bit more complicated, but again, there are some high-level points that we can use. So first of these is that, the T2 is a nice instance for dev and test, but we don't recommend that for production. For the M-class instances, these are balanced. The M4s in particular are a very good starting point for you to use with Elasticsearch. The R-class instances with more RAM provide you the ability to give you, number one, a little bit of a speed boost, and then also they provide the ability to do larger kind of queries or aggregations. Then the C-class of instance with more CPUs allows you to handle more concurrency, and then the I-class of instances has the largest attached storage. With the i3 instances, we support up to i3 16XL. These have 15 terabytes of storage each, and at our maximum data instance size of 100 data instances, you can get up to 1.5 petabytes of storage. Now, we introduced the concept of shards, and we started talking a little bit about storage and sizing. Shards themselves are what actually holds the data. And the key thing here to understand is that the shards are what do the work of Elasticsearch. So they both store the data and also they actually handle queries and updates. So when you're thinking about sizing, shards are really where you focus and concentrate to get the best distribution of shards across instances within your cluster. Again, we can start with sizing, storage, because that gives us a simple way to understand how many shards we need. So we want to set a primary shard count based on our storage. The recommendation is 40 gigabytes per primary shard. This is actually for the i3 instances, we actually recommend 90 gigabytes, but i3 instances only. So for example, for a 2 terabyte corpus, again, we have 2 terabytes of index assumed, and then we divide by 40 gigabytes to get 50 total shards primary that we should deploy for this index. You always want to use at least one replica in production. The first replica, again, is for redundancy. And then there's some evidence, and this is as we move beyond storage as driving our sizing, one of the things that we find is that the shard to vCPU ratio should be approximately 1. In other words, as I deploy instances and I count how many shards I have and I divide by my instances, I should come out with roughly the number of shards per vCPU is 1. And then another thing is you want to make sure that you can evenly divide the shards across the instances in your cluster. That will avoid hotspots for you. So if I have my 50 shards, and let's say I deploy them onto instances, I don't want to deploy them on 13 instances. That would not divide evenly. I'd rather deploy them on 10 instances, which would give me 5 shards per instance, each instance. You can use a template, which is an Elasticsearch API, and a way of specifying your shard count. And this is especially relevant in our second use case we'll get to for log analytics, but I bring it up here because it's relevant to what we're talking about. You can use a template automatically to set your shard count. So I put this template, and what it does is it specifies for every movie's anything index, then I want to set the number of shards to 50 and the number of replicas to 1. Number of replicas here just means one replica means an additional 50 shards. So new indexes which get created will match this pattern. You use this before you create your index with your data in it, and then as you're creating your index with your data in it, it will inherit these settings. You can also put mapping information in there. Mapping is the schema. Just a very high-level taste of the query API. Like the data API, the indexing API, the query API is JSON. And in this case, we have a pretty simple query. We just send query. It's a match query, so it's matching across words. And we're matching the words iron and man in the title. Now, the default operator here is an or, so you can see it's iron or man. And you can see Iron Giant, Iron Lady clearly don't have both iron and man in the title, but what they do have is a lower score because they receive only the match for iron. So with Elasticsearch, when we send queries, Elasticsearch has an inherent notion of scoring, and you'll always get a scored, sorted result set unless you choose a query that doesn't do that. And the key way that Elasticsearch works, how it handles queries, is if we think back to the field level indexes, and I send a query like iron and man, and let's say I match it against the title and the plot, right? So what Elasticsearch does is it goes with each of those terms to the field indexes for each of the fields I'm querying. If I'm querying title, it goes and it looks up iron in the title field and man in the title field. If I'm querying title and plot, it looks up iron in both title and plot field indexes and man in both title and plot indexes. It then gets the posting lists for all of those terms. Again, the posting lists just represent all of the documents that have those terms in them. So essentially, I have sets of document IDs corresponding to where the words in the query are in the documents in the index. I can then apply set arithmetic to generate the set of matches, right? So because it's an or, it's a union, so I union all of the sets together, and then that gives me a set of all of the documents that contain iron or man in the plot or title. From that match set, I then go and compute a score for each of those documents, sort it, and return that as the result. Now, Elasticsearch also, as we'll get into, is an analytics and visual tool. So this same mechanism of lookup also supports all of the visualization and features of Kibana and Elasticsearch as well. So if we think about it, once I get a result, what I can actually do is then go back to the data in the field and do some statistics on that data. This is a log analysis example because this is mostly used in log analysis, but what I have here is a search that yields a set of results, and I want a histogram of the different HTTP verbs that were in my Apache weblog. I do that, I go look at the field data for the verb for each of my results, and that gives me the set in the second column there. I can then pick out how many buckets, how many different values I have and create buckets for each of those. And then I can count how many times those occur. So get occurs 5 times, post occurs 2 times, and put occurs 1 time. This mechanism is what supports, again, all of the analytics and visualization capabilities of Elasticsearch. So let's talk quickly, one little case study for a text search use case. This is a company called MirrorWeb. They are a partner of AWS, and they were providing search across the UK government and UK Parliament web archives. They had a large set of data, it was like 120 terabytes, and they needed to get that data indexed into Elasticsearch. Now, in the past, people had done this with Hadoop and had managed to run at something like 10 million documents, 14 million documents per hour. MirrorWeb did a really great job of using AWS Spot instances to deploy a very large fleet of EC2 instances that were chewing through the data at a tremendous rate. They started out with a very large Elasticsearch service cluster so that they were able to send data in very quickly. And then once they were done, they used the scalability of the Elasticsearch service to rescale their cluster down to a much smaller cluster size and a much less costly cluster size for the ongoing running of that cluster. There is a talk from this year's reInvent, last year's reInvent actually. I have a link to that talk in the bottom there. MirrorWeb goes into much more detail about their use case. Very interesting talk. So our XYZ company now has their data in there, and they're able to search it, and their front end is roaring along, but they would like to monitor that infrastructure and make sure that they're servicing requests and figure out what's going on. So log analysis and infrastructure monitoring is another major use case for Elasticsearch. So let's have a look at how that works. In terms of architecture, within VPC, we have the application server is running, again, with Apache HTTPD on it. At the same time, we're using an open source tool called FileBeat. FileBeat tails a log file and ships log lines one at a time off to a destination that you specify. In this case, we're using Redis as a buffer, not as a cache. So Redis is receiving log lines from FileBeat, and then Logstash, another open source tool that reads from a source, formats and transforms data, enriches that data, and then ships it off to a destination. Logstash is pulling data from Redis, and in this case, again, the data is log lines. So Logstash pulls from Redis and then pushes to Elasticsearch through, again, that ENI. So this is a very common pattern that we use where we're shipping log lines to some buffer, and then Logstash or some other solution is reading them. To draw the analogy really clearly, each log line or event, depending on what your log data is, your streaming data is, each of those items constitutes a document in the same way that the Iron Man movie constituted a document for text search. And again, in the same way, that document is really, has various fields in it. And the fields contain the data that you're interested in searching or visualizing. So you can see here we've broken up this one log line into a set of different fields, including the HTTP verb, the request path, the response code, the size of the request, the requesting IP address. This is a very common pattern, especially with Apache log lines. There's actually a number of out-of-the-box open source tools that can do this kind of parsing for you. But the key point is that just like you break up your search document for the movies into fields, you break up your log line into fields. When you ingest data into Elasticsearch, you're going to go through a kind of common pipeline to complete that ingestion. And we see a number of different steps in that pipeline. First of those is we have some data sources, and we want to get the data off those sources. So we need some collection technology that's going to tail those log lines, pull that data off in some way. Then Elasticsearch, as we said, works with structured JSON. So a log line is really just a string. Something has to transform that string into structured JSON so that it can be delivered to Elasticsearch. Another step is we need to buffer that data. You can call Elasticsearch and send one document at a time, but we don't recommend that. That actually will overwhelm your cluster. So instead, you want to buffer those search documents and then send them in batches through the bulk API. Again, a number of technologies can do that for you. And then finally, you need to deliver the log lines to Elasticsearch. To give you a feel for the depth and breadth of the possibilities and how to build this ingest pipeline, here are some examples. This is not exhaustive. Some things to call out. First of all, both Kinesis and CloudWatch logs provide you with an end-to-end solution that does all of this work. So within AWS, this is one of our sort of integrations that makes it easier to get data into Elasticsearch service. Beyond that, we have a number of different technologies that allow you to do these different operations, some of them open source, some of them AWS centric. One I'll call out in particular is Lambda. So with Lambda, you can connect and receive streaming data from sources like S3 or DynamoDB streams or Kinesis. Again, you're able in there to transform that data and deliver it off to Elasticsearch. This is a pattern that is great for a dynamic situation. So either for log analysis where you're constantly receiving new data, or for the search use case where you want updates to come and flow to your Elasticsearch service domain. In contrast to what you do with a search use case, for a log analytics use case, you want to split your data into indexes that start with a pattern. And the usual ratio, usually you want to create a new index on a daily basis. So in this case, we have a pattern like logs _, and then we have a time-stamped index for each day. Depending on your volume, as I said, you'll most likely want to do this at a daily pace. If you have a very high volume of logs in the multiple terabytes a day, you'll want to do this maybe at the hourly pace. If you have very little data, in the tens of megabytes or tens of gigabytes a day, then perhaps you'll go to a weekly or monthly rotation. Depending on your ingest technology, there are different, it may do this for you automatically. Logstash does this, Kinesis Firehose does this automatically for you. The reason we do this is it simplifies the process of lifecycle management for the data in our Elasticsearch service domain. For the most part with log analysis, I'm really only interested in potentially the last 15 minutes are very important. Today's data is pretty important. 3 days ago's data is still important, but as we get older and older, specifically for logs, that data begins to lose its value. So we want to be able to age that out easily. And the way to do that in Elasticsearch is to delete off the oldest index, potentially archiving it first, at the end of each day. So I'm retaining here, I believe, 9 days of logs, usually 14 days or 7 days are usual numbers. But at the end of that each day, then I would delete my oldest index. That's the best way to do that lifecycle management. All right, let's have a quick look at the analysis portion of Elasticsearch, and we'll do that through Kibana. In this case, we're going to have Kibana talking to a proxy or a bastion within the public subnet of our VPC. That bastion will forward the traffic to Elasticsearch service through the ENI, and then provide those results back for visualization in Kibana. So I'm going to switch over to my demo screen. What I have here, I have Kibana up and running. Sorry, let's start with our search application. What I have here is our search application up and running. You can see I have some movie titles. I can search for something like Star Wars, and I'll get a list of results. This is a very common kind of UI. We've all seen it before. I can search for a bunch of things. I can search for Iron Man, and I'll find that. Iron Man 2, Iron Man, et cetera, et cetera, et cetera. Now you'll notice on the left, I've done a little bit of work here to bring forth what we call facets. These are exactly the kinds of things that we were looking at in the histogramming or the analysis that Elasticsearch does. Essentially, Elasticsearch looks at all of the search results, then counts the values in the directors field, in this case, the related actors, genres, etc. If this were a real UI, you would be able to click on each of those to filter down your search. Let's have a quick look at the code that runs that. So again, here's the PHP code. I'm using the Elasticsearch client from Elastic. I have a little function here which formats each of the search results. Nothing particularly interesting in that. I have my query here, which I'll come back to in a second. And really, to be able to talk to Elasticsearch, I simply have the host, the client, and then I search. The search itself, you can see here, we have a simple query string that's taking the keywords from the request. We're searching against the title, the plot, the actors, and the directors field. We're using and instead of or as our default operator. That means if I type Iron Man, I have to match Iron and Man. And then I'm aggregating for the genres, actors, directors, and related actors. That's really the whole PHP script. Again, this is all formatting up here. And below, we have the main body with the form in it right here. I just have my keyword field, which I pass back to the same web page. So very simple front end. This could be built out, of course, to many different levels. Now, when I make those searches, again, I have FileBeat running on my HTTP servers. So if I go over to Kibana, so you can see I have this is my main Kibana dashboard, and I'm looking at all of the output from Logstash. Kibana gives me an overview where I can look into individual search results, or log lines within Kibana, and it shows me all of my fields here and their values, like the bytes that were sent, the client IP, the message itself. Now, I have a lot of monitoring going on, so it's a little bit hard to find those two searches that I just did. But let's do this. Let's go ahead and search up here for request is star and request is wars. And I can find the request that I made. You can see here, here's my get, keyword Star Wars, etc. So this particular page also has some nice features that let you dig into your data. If I clear out this search, I wanted to show you what I can do here. Let's say I wanted to look at a more tabular version of this. So I can go look at my fields here and I can say, okay, well, let's look at the IP address of the client. So I can add that in tabular form. So I have my client IP here. And these are all the requests and what are the client IPs that made them. I could also add to this the response. And in this case, it's all 200. However, if I want to find errors, a really simple thing I can do is I can click the little minus here in the search, what do you call that, magnifying glass, and that will filter out all the results that contain 200 in the response field. So this is an easy way for me to dig in and find errors that I'm having in my search. Why did that not go? There we go. Oh, it's the wrong, I pushed the wrong thing. There it is. Okay, so let me get rid of this filter and this filter. So you can see I have a number of 404s here. Again, that's the really easy way for me to dig into my logs and find problems. Another thing I can do is I can build visualizations and I can put them into a dashboard. So I have a dashboard here, which is showing what's going on my website. Here's a breakdown of my traffic. And if I look, I have all of my traffic is the big one. These are the server status calls that I'm making. Here's the request for images, and here's the requests from users. So not much going on, but if I make a few requests here, and let's try Iron Man again, and let's try Star Wars. And let's see, we should see those pop up. So we can see here I have now some user queries came in. I have some requests for the images to serve the images that showed up. Other things I can look at some overall metrics, things like how many requests I've taken, how many clients, how many bytes I've delivered. Here's a pie chart that's showing me what are the requests I'm looking at. So slash, and here's also index.php. So these are the search ones. Here is, again, a number of different request paths that I can look at. I have a tag cloud here to show what my customers are searching for, and I have response codes here that let me monitor what's going on my site. So the green here is the 200 responses, and then I have some other ones like the 404s. So that was our demo. And I'll bring up one other customer that uses Elasticsearch for log analysis. This is Expedia. Expedia had many different groups across the company who were doing this kind of log analysis. And they needed some kind of centralized logging infrastructure that they could rely on. But they had a small group. They really didn't have a lot of people that they could dedicate to managing this infrastructure. So they started streaming all their different log sources to Amazon Elasticsearch service, CloudTrail, Docker, application logs, startup logs, and they created a centralized service that let them, from one location, dig into all of these different applications and also allowed their developers individually to dig into their own application's performance. They used Kibana to be able to visualize, just as we did, and then they were able to really find issues and troubleshoot them in real time. I gave you one example of that with the Kibana panel filtering out the 200 responses. They integrated with IAM for security, and as they're growing, they're able to feel confident that they can scale out to support their workload. So just a couple of loose ends that I wanted to mention. One of the service features, we allow you to deploy dedicated masters. Dedicated masters, well, master instances, and every cluster has a master, orchestrate the cluster. So they keep track of the instances that are in the cluster, the indexes, the shards, the schema for all of them. That master function resides on a data node. And the problem with that is if your data node becomes overloaded, then your master function can go away and your cluster can start to disintegrate. So you can deploy within Elasticsearch, and within the service, we support deploying dedicated master instances. When you do that, the master function can only be run on some of the dedicated master instances that you've deployed. So we do recommend this in production. You should use 3 because the master instance is selected based on the eligible instances, and you want to have an odd number of eligible instances so they can't split in an even way that lets them create more than one cluster. The master nodes do much less than the data nodes, so they don't have to be as large. This is our recommendations in terms of master node sizing. If you have less than 10 data nodes, then probably an M3 medium or one of the M4 large. The smaller instances are fine for that. As you scale out the number of data instances, then you begin to scale out the masters to larges, extra larges, 2 extra larges. Last thing I'll bring up is a feature called zone awareness. This is a higher availability feature. So what we do with zone awareness, you click the checkbox and we split the instances in your Elasticsearch cluster into 2 different availability zones. We make sure that the primary and the replica shards are in different zones. So in this way, you have 100% data redundancy across 2 zones. And finally, we expose a number of different CloudWatch metrics. Some of the important ones to monitor and alert on are given in this table. So the first of these is cluster status. If your cluster turns red, that means that potentially some data loss has happened. Maybe you lost 2 instances and a primary and a replica went away. We also block writes to the cluster when the disks become full. So that's one that you'll want to monitor. We expose the CPU, the JVM, and the storage as sort of the core metrics around Elasticsearch. With the CPU and the JVM memory pressure, you want to keep those less than 80%. For the CPU, it's okay to watch for 3 periods because you do get the occasional spikes. But overall, the average should stay below 80%. And then for the free storage space, we recommend that you set an alarm at 25% of the total storage that you have deployed in the cluster. That will give you plenty of time to scale up before you hit that write block exception. Last thing is we, again, take automated snapshots. You want to make sure you know if one of those fails. So XYZ Corp goes on to be a great success. They're really responsive and reactive, able to fix their infrastructure when things go wrong, able to provide great search for their customers across their movie database, and ends up, Fortune 100 company. So whether you're monitoring your infrastructure, searching application data, Elasticsearch service really makes it easy to locate and visualize the information that you're interested in. We offer ease of use, scalability, security, high availability, and compatibility with existing open source software. So we make it easy to run Elasticsearch in the AWS cloud. Thank you very much for your time. I really appreciate it.